Hello everybody, in this lecture we will provide an alternative proof for the 1996 IMO problem number 2. We will be making use of projective geometry for that. I'll prove the result in two steps. I need to first prove a small lemma, and then I can directly apply Pascal theorem to conclude, to finish the proof. So for that, I would like to start by drawing the circumcircle of our triangle ABC. So let me, why not? So something like that. So that's our circle, and let me draw our triangle here. Maybe blue color would be the best. So I have my triangle ABC here, like this. Okay, so I have triangle ABC and my point somewhere here, P. So A, P, A, B. Yeah, that's it. So I have my point P here. So to begin with, I will go ahead and extend the line BP to meet the circumcircle at the point K, and I will also extend the line CP to meet the circumcircle at the point L, and I will also extend the line AP to meet the circumcircle here at the point M, and my claim is that MK is equal to ML. So let me show it in first. So I want to show that this distance is in fact equal to this distance here. Okay, so for this focus, let's start with the angle, let's say APB, angle APB. Obviously, from the drawing, APB and KPM are vertical angles. APB and KPM are vertical angles, so KPM. But angle KPM is an external angle in triangle APK, so therefore it is equal to the sum of PKA, PKA, and PAK. Now, so angle PAK is the same thing as angle MAK, so this is simply MAK plus an angle PKA, so the second one, so this one, sorry, PKA is the same thing as BKA, angle BKA, but notice that angle BKA subtends the arc AB, but that arc is also subtended by the angle ACB, angle ACB. In a similar way, you can start with angle, instead of APB, you can start with APC. Angle APC is simply equal to, by vertical angles, I think it is LPM, angle LPM, and angle LPM, if you focus on triangle LAP, is simply equal to the sum of angle PLA and angle PAL. And now I will replace, well, PLA is the same thing as CLA, but CLA subtends arc AC, which is also subtended by CBA, plus, so PLA is equal to CLA, which is equal to CBA, and for PAL is simply equal to MAL. Now, all I will do is, from the first relationship, here, this relationship, I will just move this angle to the left hand side. So from the first one, I have angle APB minus angle ACB is equal to angle MAK. And from the second one, I will get that APC minus, and I'm just moving this one to the left hand side, angle CBA is equal to MAL. Okay, but finally notice that the left hand side, APB minus ACB, is equal to APC minus CBA by the given condition of the problem here. So as a result, angle MAK and angle MAL are equal angles. But if angle MAK and MAL are equal, so let me actually decorate these angles here. So those two angles are equivalent. They subtend these arcs here, but these arcs are tended by these two chords. As a result, those two chords must be equal. So this should imply that ML is equal to MK. So that proves the claim. So I'm done with the first part. Now in the second part, I will make use of this in my proof. So let me go ahead and redraw the circumcircle one more time using my drawing tools. I hope it would work. So something like that. That's the circumcircle of triangle ABC. So let me get my pencil again. So let me draw my triangle again. ABC. Yeah. So ABC, and then I have so this point here is M, P somewhere here. When I extend this guy, so that's P, that meets at the point K as we agreed, and when I extend this one here, that meets at the point L. And we also have shown that MK is equal to ML. So let me not mess up my picture too much, but recall that so far we know MK is equal to ML now. Okay, now let's draw the two lines that we need. So remember that we have the in circle here. So probably that's the point D somewhere there. So I'll just go ahead and draw this one. So that's the one. So D is somewhere here, D, and let's call this point where it meets the circle as point U. And now I also have the circle, the in circle of APC. So the angle, the in center is somewhere here. For the time being, I don't know if that line will go through that common point, so I'll just skip it for now. Okay, so I don't know what happens inside this box, so let's just skip it for now, and let's call this one as V. And now because we have an angle bisector here, and D, remember, was the in center, so I know that AU is equal to UK. Those arcs measure the same. And in a similar way, because this guy is equal to that one, again point E was the in center of that circle, so these two angles are equal, suggesting that this arc is equal to this arc as well. But now let me focus my attention on a new triangle, namely triangle ALK. Okay, so let me again, I don't know what's going on there, so let me just move on here. So consider triangle ALK for a minute. Notice that on this triangle ALK, U is the midpoint, V is the midpoint. So if I had to draw LU, so that's an angle bisector here, but so that angle is equal to that angle. And in a similar way, if I extend KV, that would be an angle bisector as well. But I need to be very careful. I claim that KV and LU will meet at this point here. Why is that? Because this guy is also an angle bisector here. So this point is the in center, but the in center must be because it's the in center. Notice that this angle we proved in our lemma is already equal to this sorry for that, this whole angle here, right? Do you agree? And as a result, M is the midpoint of the major arc LK, right? Or you can call it the arc LMK. M is the midpoint of this arc. That's also an angle bisector, suggesting that those two, so consider ALK on this triangle, VK, UL, and MA concur. and let's call this point of concurrence as the point S. So that's the point at point S. Okay, so we have so many points on the circle. I counted 8, maybe I'm wrong, but we will just focus on 6 of them, namely C, K, U, and V, L, B. And I would like to apply Pascal theorem on these 6 points. Consider. Let me just consider hexagon. The one that I just named, CKU, CK, CKU, VLB in that order, VLB. So notice that C and V meet. Well, okay, so skip that one for now. Okay, let's focus on, for instance, L and U. Yeah. So LU and VK meet at S. LU intersection, yeah, VK is S. And also notice that we already know that BK and LC, by construction, BK and LC, they meet at P. So therefore, given that, this implies by Pascal theorem, that BU and VC, BU intersection VC, which we call as anything, let's call it T, must be collinear with the other 2 points S and P as well. So this is the thing. So this S, P, and T are collinear. But that is exactly what was needed to be shown. Or we have now proved that these two lines meet on AP, because S and P are on the line AP, and we have basically proven that BD, CE, and AP, they all concur at this point in the middle by Pascal's theorem, and we're done.